Hey everyone, welcome to this explainer. Today, we're diving into a completely wild engineering challenge. We are going to break down, literally layer by layer, exactly what it takes to build a complex, high-stakes medical software system. Specifically, we're looking at the software hospitals use to run their radiopharmacies and nuclear medicine departments. It's this hidden world where software engineering, super strict regulations, and patient safety just completely crash into each other.
So imagine trying to run a warehouse, right? But your products are literally vanishing into thin air every single minute. That is the actual reality of a hospital's hot lab. Radioactive materials decay continuously. Unlike counting, syringes or boxes of bandages, the amount of a radioisotope you have at 8 a.m. is totally different from what you have at 10:30 a.m. So right out of the gate, this is a very unique software problem. Your inventory is a moving target governed by the laws of physics.
Okay, let's look at where this all starts. The absolute baseline for this kind of tracking often looks like this radioactive decay calculator from a program called Nucleolab, which was originally built back in Visual Basic 6.0. To build this software, you got to start with a rock-solid math module. This specific one uses a databank containing the half-lives of 43 different radioisotopes. That lets the user calculate the exact current activity of an isotope for literally any given moment, or even back-decay a source to see what it was putting out in the past. Basically, this math module is the beating heart of the whole shebang.
All right, so Layer 1, Math and Decay Constraints. Let's get into it. And this brilliantly illustrates the core problem of this first layer. You have to perfectly match that vanishing inventory with the exact doses a patient actually needs. Because the radioactive concentration is constantly dropping, the physical volume of the liquid you need to inject has to increase over time to get the exact same dose. So the software can't just calculate current activity. It has to calculate the exact fluid volumes needed for future appointment times. If a patient is scheduled for 9:20 a.m., the software has to tell the tech the exact volume to draw into the syringe based on the starting activity and the exact time of dispensation. It completely eliminates those laborious and frankly error-prone manual calculations.
Moving right along to Layer 2, Surviving Strict Inspections.
Okay, so once you've got the math nailed down, you aren't just building a calculator anymore. You are building a massive compliance engine because the hospital's licenses to even handle radioactive material are literally on the line here. These departments are heavily scrutinized by the Nuclear Regulatory Commission or local agreement states, and developers need to know exactly what these inspectors love to look for. They want the dose calibrator quality control logbooks. They want incoming package records with lot numbers, personnel monitoring data, and highly restricted logs for things like high-dose iodine-131 therapies. Your software must track all of this automatically, creating an absolutely ironclad digital paper trail.
And then there are the rigid, step-by-step safety protocols the software has to enforce. Think about this. Every single day, users have to survey rooms with a Geiger-Müller counter and record the background and actual readings. Weekly, they're doing 5 to 7 dry wipes across the facility with an open energy window just to catch unexpected spills. Plus, every 6 months, all sealed calibration sources get leak tested. The software has to track these schedules, alert users before they're overdue, and lock in the results. If there's contamination, the system literally forces the user to document the hotspot, clean it, and record the new safe reading.
Which brings us to this absolutely wild, surprising number, 1 curie. The software actually has to track all the radioactive waste poured down the designated hot sink. And the standard limit for an entire hospital, it's usually just 1 curie per year for all combined liquid waste. To put that into perspective, the software has to tally up every single microdose poured down the drain across all users and trigger automated alerts to make sure the hospital doesn't breach this massive regulatory limit. Crazy, right?
All right, Layer 3, Connecting the Digital Hospital.
So a hot lab doesn't just exist in a vacuum. It's got to talk to the whole hospital's IT infrastructure, meaning our software needs translators. The crucial point here is understanding the baseline standards, starting with DICOM, Digital Imaging and Communications in Medicine. This is the universal language connecting imaging modalities, PACS systems, and scanning hardware. For our tracking software, tapping into the DICOM modality work list means pulling patient data straight from the hospital's main system, right into the hot lab seamlessly. And that brings us to the 2 heavy hitters for data interfaces, HL7 and DICOM. Now, DICOM modality worklist is great because it's basically plug and play. It yanks the patient's schedule and room numbers right into the software with barely any custom coding. But HL7? HL7 is the real powerhouse here.
It acts like a two-way street. Not only does it pull patient data to stop dangerous transcription errors, but it actually fires the exact administered dose, the radioisotope used, and the injection time right back into the hospital's main radiology information system.
Layer 4, securing against cyber threats. Now, all that amazing hospital connectivity, it leads to a pretty terrifying reality. We are not just talking about stolen passwords here. In healthcare IT, cybersecurity is directly tied to physical patient safety. If a medical device or the software monitoring it gets hit by malware, the safety features can be manipulated. That could shut down hospital operations or, worse, cause direct physical harm to a patient.
Just to show you how serious regulators take this, listen to this direct warning from the FDA. They flagged exploitable vulnerabilities in radiofrequency-enabled implantable cardiac devices. Think about that. Even the most advanced, life-saving hardware on the planet is completely vulnerable to intrusions if the software environment around it isn't meticulously hardened against exploits.
So for developers, this means actively dodging some absolutely catastrophic coding errors. You cannot have hard-coded passwords for maintenance personnel. No plain text authentication, period. You have to sanitize databases to block SQL injection attacks. And maybe most importantly, you need a solid lifecycle plan for security patches, especially since hospitals are notorious for keeping unpatched, ancient legacy devices hooked up to their networks for literally years.
Now, what's really interesting here is the unique tension developers face. Standard IT security is all about confidentiality, keeping the data locked down, but medical device security also has to heavily prioritize availability and safety. Like, if a ransomware attack hits the hospital, the tracking software must still fail safely so patients needing urgent radiation therapies aren't just left in the dark. It's this massive balancing act between locking data uptight and keeping life-saving systems online.
Which brings us to our final layer, Layer 5, quality control and validation. Okay, so you built the math, the compliance checks, the network, the security walls, awesome. Now, how do you prove it actually works without hurting the patient workflow? Well, you have to understand that this software isn't just an app you download. It is legally classified as a regulated medical device. Under both EU and FDA directives, nuclear medicine software has to be rigorously validated before it ever touches a hospital. That means a strict software lifecycle, highly documented user requirements, and intense risk assessments.
In the industry, this is broken down by GAMP risk categories. That's good automated manufacturing practice. Basic IT stuff, like an operating system, is a low-risk Category 1. But patient dosimetry software, like that decay calculator we saw earlier, that shoots right up to Category 3 or 4. It comes with huge testing burdens, bug reporting protocols, and strict functional tests during installation just to prove those algorithms are completely flawless. And here is why all this testing matters. The highest risk software failures aren't always giant, fiery system crashes. It could be something as mundane as an incorrect system time setting. Remember, our inventory is decaying by the minute. If the server clock is off by even a tiny bit, every single decay calculation gets ruined. That leads to incorrect dosages being drawn up and injected into patients. A minor bug can totally alter an exam result.
So, what does this all mean? Building radioisotope tracking software is just a massive feat of engineering. But a solid blueprint isn't really about passing a state inspection or dodging a fine, is it? It's about safely managing the future of healthcare IT. Is the software just checking a regulatory box, or is it an active, secure participant in saving patient lives? Thanks for joining me on this explainer. I really hope this breakdown completely changes how you view the software running quietly in the background of our hospitals. Catch you next time.